In this video, we're going to be looking at the definition of a logarithm. To begin with, we're going to look at a few different types of equations. So first of all, as you notice, each of these equations, we have an x, or the variable, in the exponent, which means these would technically be exponential equations. So if they are exponential equations, one thing that we know we can do to be able to solve is we have to make sure that the bases are the same. So for first example, they're the same. Second example, they are not. And the third example, they're not. So first one's pretty simple in that all you need to do is get rid of the bases and set the exponents equal to each other to be able to solve. For the second one, you need to make the base of 27 here, you need to have that be the same as a base of 3. And we know that 27 is the same thing as 3 to the third, and so that's what we're going to use to help solve this one. So you write it as 3 to the third equals 3 to the third to the x plus 1 equals 3 to the 2x minus 7. Make sure you do your distributive property with that 3 here, 3 times x and 3 times 1, and you end up with 3x plus 3, and then you can solve. For the final one, we don't have any exponent over here. However, you still need to write this 81 with a base of 3. 81 is the same thing as 3 to the fourth, so this one actually turns into be a pretty simple problem because we have 3 to the x equals 3 to the fourth, and so therefore x equals 4. However, if we just change it just ever so slightly, instead of having 81 here, you had an 80, this problem would be more complicated because there is no nice exponent that you can write 3 to the power of in order to end up with 3 to the x on the other side and be able to cancel out those bases. So what do you do? We need a new type of equation. So up until now, we haven't had any sort of type of equation to undo or to do the inverse of an exponential equation, and that's what we're going to look at in this video. So first of all, we're going to spend some time thinking again about the exponential equation. So if we have y equals 3 to the x, the equation we had before, quick way to set this up is to start with the graph. And so you make a table, -2 until 2 in that table, and then you just plug those values in here. 3 to the -2 is going to be the same thing as 1 over 9, because remember a negative exponent flips that base into the bottom, or flips it to the other side. In this scenario, it's to the bottom. So you have 1/9, 1/3, 1, 3, and 9. And so as you plot all those points, you can see what your exponential equation looks like. So if I were to want to talk about the inverse equation, what we do know is that an inverse will always flip everything over the y equals x line. So all of these coordinate points that we have over here with this exponential equation, we're going to flip to create this table for its inverse. So instead of listing out -2, -1, 0, 1, and 2 down this x, I'm going to be a little bit smarter and use this set of values. So if I just flip those using what we know about inverses, we would end up with 1/9 as my x, 1/3, so on and so forth, and then the corresponding flip of those particular x values. So now when we plot these points, we end up with a graph that kind of looks like this. And if we think about how this horizontal asymptote of our exponential equation is going to come out to look over here with these points, we would have this as our graph. And you can see that those flip over that y equals x line nicely to create this inverse graph. This equation is the equation of what we call the logarithm, with a log base of 3. And so this type of equation is a logarithmic equation, or a logarithm. The equation looks like this, where you have y equals log, and then base 3 of x. So the base of 3 here is the inverse of this equation over here, because this also had a base of 3. So it's important that you use that vocabulary. So y equals log base b is a logarithmic equation, log base b of x. So this x is not in the base. This x is also not in the exponent. It is just sitting right next to it, and it's like it is the input. So I could put a set of parentheses here. You might see that on your calculator, or on occasion where you have log base b of x. That's where that of comes into play. The domain of our logarithm is x is greater than 0, as we saw with our previous graph, and the range is all reals, and there is a vertical asymptote at x equals 0. This graph is the inverse of an exponential with a base of b. In order for two equations to be inverses of each other, they have to undo each other. Logarithms and exponentials undo each other if their base is the same. So as we take a look at that, we've also done some work with inverses, and we've talked about how we have f of x and the inverse of f of x. So here we have a log base 8 of x, and then the exponential equation with the base of 8. So if you do your composition, as we've done in previous learning activities, where the inverse goes in for f, then you have log base 8 of 8 to the x, or if you flip it around, you do 8 to the log base 8 of x. Those log base 8 and the 8 to the part are going to just cancel each other right out. And so that's how you end up with just x. Again, exponentials and logarithms undo each other as long as their bases are the same. So back to our example, where we started with 3 to the x equals 80. We know that we can do the inverse of this 3 to the x by doing a logarithm now. So I'm going to do the logarithm of both sides, just like you would square both sides or square root both sides. Here we're going to do the log base 3 of both sides. So you have this 3 to the x and then the 80. They are now the inputs of our logarithm. So log base 3 of x, of 3 to the x. So as we said earlier, that log base 3 and the 3 to the part is going to cancel each other out. And so you have x equals log base 3 of 80. And that would be our answer. Right? So the output of a logarithm is the exponent of the base that gives you that. So I'll say that one more time. The output of your logarithm, so whatever I would get out from this value, it's not a numeric value yet, but it is the answer. Whatever I get out from that is the exponent of this base that gives you 80. Right? So 3 to the log base 3 of 80 would cancel out, and you'd just get that 80 there. So yeah, that's the answer. That's what it looks like. It's in logarithm form, and so we want to find a numerical value. We need a few more concepts. So to finish, we could use logarithm tables, which are complex and complicated. That's what people used to use before we had the use of calculators. But since we do have a calculator, we're going to use our log base 10 key, which can be found right on your calculator here, where you have log in this spot. So that's on the bottom left side. So you're going to use log base 10 key, and you can use that to calculate. So you have log base 10 of 10,000 is the same thing as log of 10,000. So anytime you have a base of 10, you don't even need to write that base in your logarithm. You just have a log sitting there, so you have log of 10,000 is the same thing as log base 10 of 10,000. Same thing here. If you had log base 10 of 485, you could just write log of 485. So just keep in mind, anytime there's no base written, it's automatically always implied that it is a base of 10. And if you just type that into your calculator, log of 10,000, you'll get 4, right? Because this is a base of 10. So what we're really asking you is what power of 10 gives you 10,000? 10 to the 4th power is 10,000 because there are 4 zeros there. But it's a little more difficult here where you have this base 10. 10 to the 2.6857 is 485. That's what we're finding with a logarithm. So to help you find that numerical value of the logarithm, we're going to use that base 10 and our calculator, and finally the change of base formula, which is what you use in order to calculate this. For any logarithm with any base of any value, you can always change it into a ratio of 2 logarithms as long as that base that you use is the same. So yeah, that base here can be any value, but we tend to use a base of 10 because we want to do the work on our calculator, and we have a nice base 10 button on our calculator. So the base always goes in the bottom with that logarithm. So base in the bottom, and whatever's here goes in the top. So if you had log base 3 of 80, then the base would go in the bottom here, where you have log base 10 of 3. The 80 will go in the top, where you have log base 10 of 80. And all you need to do is type this ratio on your calculator. So you do log base 10 of 80 on the calculator, do log base 10 of 3 on the calculator, and then you divide those, and you'll end up with your decimal value, 3.9887. So what that means is that 3 to the 3.9887 is equal to 80. So that's what the logarithm tells us. What power of 3 gives you 80? Because that was the original question. The original question was 3 to the what power was equal to 80. Well, now we know that x, that power, is just underneath 4, which made sense because earlier 3 to the 4th was equal to 81. So if we want this to be just a little bit smaller, the exponent has to be a little bit smaller. What is it exactly? The logarithm tells you, and it's 3.9887.